This video is the fifth part of a series showing how RoadEng can be used for design review for the Korean Forest Service when provided with a DWG that contains 3D contours and 2D alignment information. Now, this fifth part is going to be an extension beyond just the conventional review, and we are going to use some of Softtree's optimization tools to evaluate design alternatives. So this workflow is looking at it through the lens of a review and alternatives, but it can be adopted for designs that are completed from scratch. Now, this part of the workflow is picking up just following video 1, where we've created our terrain surface and we have our previously designed alignment in place as a centerline feature. So we could click the Optimization tab, click Path Explorer AI, and we could run the tool as is, and the software would consider our unit costs for our earthworks. Now in this case, I'd also like to consider the expected costs for dealing with my crossings in this. So we can add additional costs to features. So those can be costs, they can also be no-go zones. So in this case, to generate those streams, I'm going to click Terrain Modeling, click Streams and Ponds, and I'll run our Streams and Ponds feature to generate expected stream location. Next, I'm going to click my centerline, so it's my currently selected feature, and I'm going to click the Optimization tab. I'm going to click Path Explorer AI, and I'm going to begin to configure my optimization. Now, with this, we have our currently selected feature. We could control the approach directions if we had to in this, but I don't think it's necessary in this case. We can leave that unconstrained. Next, we're going to add in some driving constraints that are going to influence where the road goes. So big ones like horizontal radius, we're going to change our resolution. We'll go with a resolution of 5. We can use a road width of whatever we'd like. I'll keep this as is. And I'm going to assign my grade constraints. So in this case, we'll look at it through the lens of we want a grade that's no steeper than 14% favorable and no steeper than -12 adverse. So we could run that as is, but we're going to add in a couple extra construction zones. First, I'm going to add in a no-go polyline, and I'm going to use this area of interest feature that we use to thin our data, and by adding that in as a no-go polyline, the software is not going to leave that polygon. So that functionality is useful to make the problem smaller, so it solves quicker. And it's also useful if you have things like property boundaries that you'd like to adhere to, or terrain stability concerns where you can't cross certain portions of the hill. Rather than a no-go feature, we are going to next add in a, well, it could be a polygon or a polyline. We'll go polylines, and we are going to add in the stream features. So we have those selected, and we're going to say they are going to cost about $3,000 a piece when we cross them. We'll hit OK, then we'll hit OK. And we'll let this run. So here it said it's found 5 paths. It's looking for better alternatives. So we'll let it continue to look until it says it's unlikely to improve. So here it says it's unlikely to improve. We'll hit cancel and we'll see the options that it's provided us. So there we are. We can see our options. Now if we'd like to weigh these options against each other, we can right click, select feature by name. Oops. And we can see XPath feature with a number after it. Now the number after it is the expected cost given the parameters that we've put in. So this alignment here is our expected cheapest solution given the geometry that we've specified. I'm going to save this terrain file, and we'll continue along in the location module to further refine it. So just like when we set up a conventional design, we're going to create a new file. We're going to reference our topo that we've just saved. Here, instead of using the original DWG line work, we're going to use that XPath feature. So we can select whatever lines we'd like to start with. And we can see our alignment is started. Next, we could change our cross-section template if we'd like. I'll just continue working with the default here. And an optional step here that's going to make the design a little lighter and easier to work with is to assign curves at all of the curves. So right now this alignment's a polyline, and we'll turn it into a proper alignment with curves by using our curves and tangents tool. Or sorry, polyline to alignment. Here we'll put in our minimum radius. We'll leave a tolerance so the software can find that line of best fit with some deviation, and we'll hit OK. So now, instead of having a series of curves and tangents, we can see we have proper curves in our alignment. Here I'm going to make an additional change. And I'm going to increase our cross-section sample spacing to smooth out my line work on the edges here. There we are. So currently we have our geometry for our horizontal alignment, and just like we did before, we can use the vertical optimizer to find the cheapest vertical alignment for our project. So here I'm going to add in my design constraints, and I'll use the same ones as I used before. So a favorable grade of 14, max adverse grade of 12. I can set my K values to be whatever I'd like. I'll hit Add Edit. If there's control points I'd like to account for, I can add those in. And in this case, I won't use my full bench constraint. We'll see how it does if I allow fill. We'll hit Process, and we'll run our optimization. We'll hit OK. And we can see the alignment that we're working with, and we can review it just as we would in video 4. So here we can see, since we're allowing cuts and fills, we have a balanced mass hull rather than one that consistently climbs. But if you want to deter large fills like that, we could again assign full bench constraints as needed. Thank you.